NASA's future projects will involve manned flight deeper into space than even before. Astronauts involved in future missions to the Moon, cislunar space, asteroids, and ultimately Mars and beyond will face periods of strenuous activity during extravehicular activities. Such EVA activities may involve building of structures or conducting surface exploration of planetary bodies. Here at Kansas State University, we are developing a wireless biosensor network capable of advanced health monitoring to keep those future explorers safe. In this video, we focus on one task in 5-part project. Task 2. Learning how wireless signals interact with an astronaut spacesuit, which itself is sometimes considered the world's smallest spacecraft. Task 2 focuses on incorporating a wireless network into the spacesuit. But first, we must know the medium through which the signal will travel. Following measurements on the retired Apollo A7L spacesuits at Kansas Cosmosphere, K-State's Apparel and Textiles and Interior Designer Department built a model of a modern EMU spacesuit using the materials we obtained from NASA's spacesuit builder, ILC Dover. The spacesuit has metallized layers for thermal insulation and micrometeoroid protection, but metal blocks radio waves. So how can a wireless network be built? Electrical and computer engineering students have designed a top hat antenna to launch and receive the radio signals within the suit. This is essentially a miniaturized version of the WWVB radio antenna that keeps your automatic clocks in sync. That radio works at 60 kHz. Ours operate around 400 MHz, or about 7,000 times higher, allowing the antenna to be 7,000 times smaller. We built these antennas into radio transmitter and receiver hardware to test our network. The in-suit radio frequency propagation was tested by putting the transmitter and receiver at different locations specified by the KSU Department of Kinesiology on a related task. These locations are suitable for the astronauts' health conditions monitoring, such as muscle fatigue, heart rate, whole body metabolic rate, oxygen intake, carbon dioxide production, and ventilation. To determine the signal strength, the radio signals received information was transferred into an audible sound using 555 timer used as an audio oscillator. Using the microphone, we get to determine the frequency of the sound on an oscilloscope using the fast Fourier transform. It may not be elegant, but it solves a key problem: how to get the information out of the suit. For all these measurements, the body of the astronaut was covered with the 2 layers of the sweatshirts and sweatpants to maintain an approximate air gap between the suit and the body. Another issue that students are studying involves how to power the radios in the oxygen-rich environment of the suit. Instead of using batteries that could produce dangerous sparks, the research team is using the energy harvesting as the alternative. This research focuses on thermoelectric energy harvesting, which produces energy using the temperature difference between the human skin and the liquid cooling and ventilation garment that astronaut wears to keep from overheating.